Welcome. The purpose of this video is to show how Minkowski spacetime can be used to help visualize Silberstein-Thomas Wigner rotation with a focus on direction, including the related Thomas Precession. You may be watching for different reasons, but more than likely you are studying the Wigner rotation and you're looking for a little bit of extra help visualizing it. In this video, assumptions are made to simplify the content. Some effects are ignored, such as perspective, color changes from relativistic redshift, relativistic Doppler and beaming effects, and even apparent rotation, such as the Terrell-Penrose rotation. The assumption is that the viewer has a basic understanding of special relativity. To start, in the initial setup, we'll assume that the Earth is a true inertial reference frame, sigma, at rest with our observer. We'll consider two spatial axes. Rocket A is aligned with the x-axis, and rocket B is aligned with the y-axis, along with a set of scales aligned with these axes. Our experiment is confined to the xy plane so that we can reserve the third axis for time. The first boost U is along the positive x-axis to a new reference frame, sigma prime. Consider the boost instantaneous. Rocket A accelerates both rockets and scales to half of the speed of light, with a length contraction along the x-axis relative to the Earth or sigma frame. From the new sigma prime frame of reference, we have the opposite story as shown. The Earth appears contracted relative to the rest frame of sigma prime. At this point, let's set up a simple Hermann-Minkowski spacetime. The velocity vector u for rocket A is shown here from the origin to point A1 at reference time and distance shown. The factor L allows us to scale the magnitude to the size of our rockets. A plane through A1 shown is simultaneous to observers at rest with rocket A in sigma prime. The axis of proper time shown is also a world line for the thruster end of rocket A. Axis A prime shown is simultaneous for rocket A only at event A1. Line B represents the world line of the nose end of rocket A. Add key events along the world line for the nose cone for points B1 through B4. Add sigma reference coordinates now to point A1 to compare to sigma prime. Note that it is not correct to align the rocket image to any specific Minkowski axes, because the diagram only represents a 2D slice through space-time. What is observed depends on the simultaneity of the rest frame that the image is observed from. Remember, we're making simplified assumptions, no aberration, Doppler shift, etc. Let's add a few more things to help us understand Minkowski spacetime. A light cone in green, outward light perpendicular to x prime in sigma prime, a light ray from B1 to A1 and then from A1 to B4, and then we'll add dimensions aligned along the x-axis. The Minkowski diagram may look more familiar as the profile view of the xt plane. Point B1 to A1 follows a reversed light cone from the nose cone of the rocket to the thruster. Light travels a distance of 0.5774 times the factor L, while the rocket travels half that distance in the same time. Point A1 to B4 follows along the light cone shown and represents light from the thruster back to the nose cone of the rocket. The rocket is contracted to 0.866 times L in the sigma frame, and the light travels twice this distance along X to reach the cone. Those two segments represent a longitudinal light clock. A transverse light clock is usually used to explain time dilation. Segments from B1 to B3, then B3 to B4, would require a delta y component along the y-axis to explain the longer path of light in the rocket relative to the sigma frame. For both longitudinal and transverse cases, the round-trip path takes 2.3 times L as compared to 2 times L in the rest frame of the rocket. The rocket is length contracted in the sigma reference frame as the span from A1 to B2. However, what is simultaneous to the rest frame of the rocket in sigma prime is different. The span between A1 and B3 in the Minkowski spacetime is the inverse of the length contraction along the x-axis relative to the sigma reference frame. Simultaneity is important for the Wigner rotation, as we will see. Let's revisit the complementary rocket frame sigma prime from earlier, which is the rest frame for rocket A. From the rest frame of rocket A, sigma prime, which is moving with velocity u relative to sigma, we will now boost rocket B by a velocity v to a new frame, sigma double prime. X prime is collinear with the x-axis, and y prime is parallel to the y-axis. Rocket B is boosted relative to rocket A 90 degrees from the x prime axis. This is important because both direction and speed of velocity are relative, in this case to sigma prime. In this setup, rocket B boost V is relative to rocket A in sigma prime. Both the Earth in sigma and rocket B in a new frame sigma double prime are length contracted along their respective vector of motion relative to rocket A. And if both boosts occur simultaneously and instantaneously, then the apparent trajectories will have the symmetric geometry as shown relative to rocket A in sigma prime. Hopefully the relativity is clear to this point, because next is where things get really weird. The same boosts now relative to the Earth reference sigma show a different story. The geometry is not the same 45-degree symmetric relationship seen in sigma prime. The y component of rocket B's velocity is reduced relative to the Earth reference. Rocket B is length contracted along both x and y axes. The velocity addition formula for the vector form of u and v describes the relative rocket B trajectory shown, but considers v relative to sigma prime as shown in the previous slide. In the case shown, x double prime skews from x by 16.1 degrees. Where did that come from? This is not the 8.2 degrees we're expecting from the STW or Wigner rotation. One formula to calculate this rotation is shown. Just for curiosity, let's step back and take a look at the complementary view of a Wigner-rotated Earth from the rest frame of rocket B in the sigma double prime frame. Here, the 16.1 degree skew is from the polar axis of Earth in this case. But let's focus on the one case where rocket B is skewed from the rest frame of Earth. Why do the scales and the second rocket B skew that way? And where is the Wigner rotation? To explain the skew, we'll revisit Minkowski spacetime. Remove the light cone and add a sigma XY reference frame at A1. Then next, we'll add the second boost V, but from the sigma frame, we'll call it W. The delta XY components of W are derived from the velocity addition formula shown earlier. The trajectory is clearly 4.1 degrees from the expected 45 degrees of the frame sigma prime. Still, no 8.2 degree Wigner rotation. Keep points A1, B2, and B3. Add point A2 representing the thruster end of rocket A simultaneous to B3 in sigma. Add point C3 representing the origin of the x double prime axis shown. Move the XY reference plane to A2. Rocket B and scales aligned with sigma prime are compared to the sigma reference. Here is a top view of the diagram aligned with reference time. Note that the x double prime axis in purple is skewed relative to the x-axis in red because the sigma double prime frame disagrees with sigma on when the world lines defining the points along x double prime are simultaneous. Still, there is no 8.2 degree rotation, but we'll see how the angle skew is relevant. Note that x double prime simultaneous to the frame sigma prime is parallel to x. But simultaneous to sigma, where C3 is later than A1 along W, is not parallel to x. Compare the scales along with rocket B relative to the Earth frame sigma, and look again at the double-boosted system. What if now we boost a third rocket C with its own set of scales directly along the vector W from Earth? This rocket C and its scales are length contracted to 75% along the vector W based on 66% C. Clearly, we have what looks like a rotation between the orientation of the scales of the direct path along W with rocket C versus the double-boosted U plus V path with rocket B. Aha! Wigner rotation at last. Not exactly, but we're almost there. Compare to the XY reference axes at C3. Next, compare to the single boost axes of rocket C contracted along W, aligned with the scales moving with rocket C. In our case, from the reference frame of the Earth, the angle between the single boost axes along W and the double boost U plus V axes measures 7.89 degrees, not 8.21 degrees. But why? Because the axes and scales are length contracted in sigma along W. To observe the Wigner rotation, we need to observe the comparison of the axes in their rest frame of reference, sigma double prime. In Minkowski spacetime, we need to bring the simultaneity of W to the rest frame. If the rest observer is boosted from the Earth frame sigma along W to the sigma double prime frame, the correct rotation becomes evident. Finally, we see the 8.21 degree Wigner rotation in the frame of sigma double prime, in the clockwise direction. Note that the angle between x double prime and x holds 16.1 degrees from both frames to maintain symmetry. With our boost sequence U plus V axes orientation in purple, we need a single boost W, the blue axes, plus a Wigner rotation 8.21 degrees clockwise to duplicate the U plus V boosted frame. To be clear about the direction of rotation, use the right-hand rule. Here, the index finger represents the x-axis, the middle finger at 90 degrees is the y-axis, then the thumb represents the z-axis as shown. Another version of the same rule considers the palm for the y-axis, where the fingers usually represent field vectors. And the fingers curl counterclockwise in the xy plane for positive rotation in the plus z direction. But in our case, the Wigner rotation was clockwise, or in the negative z direction. You might be tempted to jump right into the Thomas Precession, swapping out rockets for electrons and the Earth for a nucleus. But hold on. Depictions of the electron are sketchy endeavors at best, and to simplify, we use analogies to physical objects. Also, please note there's a huge disclaimer. We're not covering quantum mechanics in this presentation, and there are some conflicting views about the Thomas Precession. Please check the notes in the description. Consider U as the tangential velocity of a Bohr-like electron orbit, and instead of V, use an incremental change in V over an incremental change in time. Acceleration toward the center is orthogonal in the lab frame, sigma, then assumed orthogonal in the instantaneous electron rest frame, sigma prime, for infinitesimal changes in time. In the lab frame sigma, the acceleration a is observed as dvy divided by dt. For the electron frame sigma prime, this is gamma u times dvy prime divided by d tau. We need to make sure that we correctly account for the effects of special relativity in these components of the equation. Starting with Stapp's formula, sine theta approaches unity. Gamma 2 approaches unity, and gamma 1, 2 approaches gamma 1. Simplify the equation by factoring out the terms. V1 is the momentary tangent speed, u. V2 approaches gamma u times the incremental change in speed of boost v divided by the change in reference time. Omega also changes incrementally with change in time. For small change in omega, sine d omega approaches d omega. Factor out the Lorentz factor of the tangent speed. In general, the cross product between u and a applies. Then the Thomas Precession simplifies in the lab frame to the familiar form shown. Pay special attention to the minus sign. Because of the right-hand rule, the sign is flipped if the order of acceleration and orbital velocity are flipped. Suppose a spinning ball description of the electron to help describe the mechanism. Consider an orientation of the electron spin axis related to its angular momentum. Now introduce an off-axis magnetic field to induce a torque on the electron. Instead of the spin axis aligning with the magnetic field, the torque induces a Larmor precession. In a system where we've assumed a ballistic-like electron has a counterclockwise orbit with a counterclockwise Larmor precession, the opposing clockwise effect of the Thomas precession will reduce or counter the Larmor precession, but will not affect the orbital velocity. However, the total energy of the system would be affected by these relativistic effects. This concludes the presentation. Hopefully you found this visualization useful by using Minkowski spacetime to help gain an understanding of the relativistic Silberstein-Thomas Wigner rotation induced from two non-collinear boosts, with special focus on the direction of the effect, and how this effect could relate to the Thomas precession in a kinematical way using only Einstein's special relativity.